Hello and welcome to a new video series on RSA encryption, and I'm going to try make a couple videos on just how to implement RSA, but also you shouldn't really ever try to use it in production because it's probably going to be not secure. However, it's just really good to understand it. It's quite interesting as well, and this video I just want to give like a brief overview of what we really need to do for RSA to work. So what RSA is an asymmetric encryption algorithm. So usually when you learn about, like, for example, Caesar cipher, or even like the Veronum cipher or the Enigma machine, all of those are symmetric encryption algorithms. They use one key and then the same key to decode your ciphertext. Whereas in asymmetric, you have a private and a public key. You encrypt using the public key. Everyone has the public key. Everyone can encrypt a message for you, and then they can send it to you, and only you can decrypt it. Yeah, it's kind of like a letterbox where you can only put stuff in, but you can't take stuff out unless you have the key, the private key. But anyway, I don't know how good that analogy is. And RSA is an implementation of this. It's probably one of the most popular ones. Well, probably the most studied one. Anyway, for this to work, it kind of relies on two things, which is number theory and prime numbers, and modular arithmetic. So first thing we're going to have to do is generate prime numbers. We need to generate two prime numbers, and the size of these prime numbers, from my research that I've done, the size of these prime numbers should be around 2048 bits, maybe 124 bits. And that will allow us to encrypt around 500 bytes in our RSA. So we need to generate two prime numbers. And the way this is usually done are using primality tests. And some of these are probabilistic. So a primality test is an algorithm which will tell you whether a number is prime. And first of all, when we generate primes, the naive approach is basically to generate every single possible prime up to like 2 to the 248. If we want a 248-bit prime, then that's what we're going to do. Well, that's what we might think we should do. However, simply looping for that long will take an eternity. So instead, what we end up doing is we end up generating random numbers, usually random odd numbers, making sure the last bit is a 1. Because if it's not a 1, then it's pretty trivial to show that it's not prime. And a primality test is an algorithm that tells us whether the number we've randomly generated is prime or not. So we kind of guess, and then we test whether a number is prime. And for primality tests, there are two types, deterministic and non-deterministic. Non-deterministic primality tests tell you whether a number is prime with a certain probability. However, they're very useful since they're a lot faster than deterministic ones usually, but obviously there's a chance that they're wrong. Okay, so we generate two prime numbers using a primality test, and in this video series we're gonna use the Rabin-Miller primality test. The Rabin-Miller primality test. I think this one has it's got some heavy number theory background, but understanding it is quite nice. We're gonna have to learn a little bit about Fermat's Little theorem. His last theorem is probably a lot more popular than his Little's theorem, but his Little theorem is very much useful. And we're gonna learn a little bit about modular arithmetic, which will come in handy for the next stage. So we generate two prime numbers, and we feed this into our algorithm for RSA key generation, and we want our output to be two private keys and two public keys, or a pair, two pairs, each with a private and a public key. Yeah. No, I just realized this is completely wrong. This is completely wrong. You're gonna have just one public key and one private key. Yeah. It's just because when you basically every key consists of like a tuple of two numbers, which I'll explain later in the videos, and you use it to encrypt and decrypt. Anyway, for this we will need something called extended not Euclid's. I keep saying Euclid's. It's Euclidean algorithm. This is a very interesting algorithm. It's really basic to understand, but I wouldn't say it's like that trivial to code. It's quite. Oh, what have I done? Yeah, it's quite easy to understand. I think you could probably explain this to like a 9-year-old, and they'd follow it quite well. But it gets quite heavy on the implementation. Not heavy, but I feel like it's not trivial to implement it. So yeah, the output of our key generation is a tuple, sorry, a pair of tuples, which each pair represents. I'm explaining this really badly, aren't I? But we'll see in the next video. This is just going to be a private and a public key, and we're going to have two algorithms, which are going to be quite small, to encrypt and to decrypt. And yeah, the decrypt algorithm is going to take the private key, and the encrypt is going to take the public key. And pretty much, we're going to encrypt the message and just send it over as bytes, usually over like sockets or network, like a TCP connection. And then the receiver is going to decrypt that message, and that's usually how communication occurs. Yeah, RSA is quite slow, so you usually wouldn't do this for stuff like images. But a nice thing about this that you actually end up avoiding the what was the problem? There's the key problem with symmetric encryption. So basically, you don't have to send the key across. You can send the public key across, which doesn't allow you to decrypt. Anyway, yeah, that was a pretty bad explanation, but we'll get into a lot more detail in the next videos.